In the next couple of videos, we're going to work a few examples of circuit analysis techniques that you covered in your Circuits 1 class. We'll talk about how to do Thevenin and Norton equivalent circuits. We'll do an example of the node voltage method, and we'll do an example of the mesh current method. And as you'll see, like everything we've done so far with phasors, the techniques are exactly the same as they are for you in Circuits 1. So there's nothing really new there, but we're just going to work a few examples just to kind of reinforce those concepts. And I'll break them out into separate videos. And so with that, I guess, let's just jump right in. Let's take a look at Thevenin equivalent circuits. So in this example, we're given a circuit with a bunch of different impedance elements, a voltage source, and we're asked to find the voltage here at the output terminals of this circuit. And as you can see, we're going to use Thevenin equivalent circuits, Thevenin and Norton equivalent circuits to solve this. So the first thing we'll notice is that we have, you can circle it right here, a Thevenin circuit right there. And it's in parallel with this 9 ohm to J3 ohm impedance circuit as well. So what we're going to do is convert this first into a Norton equivalent circuit. So let's go ahead and do that. We'll turn it into a current source with some current I, which we'll calculate here in a second. And then we just bring those values, those resistors, those impedance values down with us. So that'll be 1 ohm and J3 ohms. And that's in parallel now with this 9 ohm resistor and this minus J3 ohm capacitor. And that's in series with the rest of the circuit. We won't worry about that just yet. The next thing we need to do is calculate what our I is. And so to do that, we just rely on Ohm's law. So our I is equal to V over R. So it's going to be equal to just the 40 over R, which was 1 plus J3 omega. So what that means is we've got to, use that complex conjugate thing like we've done in the past. 1 minus J3 over 1 minus J3. And like I've been doing, I'll let you go ahead and finish that arithmetic. But when you wrap it up, you should get that I is equal to 4 minus J 12 amps for I. So that's going to be 4 minus J 12 amps. The next thing we need to do is find our equivalent impedance by combining these two sets of impedances in parallel. I'm going to go ahead and call that our Z sub n for Norton, since that's going to be part of our Norton equivalent circuit. And that'll just be these two guys in parallel. So 1 plus J3 times 9 minus J3 over 1 plus J3. 1 plus J3 plus 9 minus J3. And when you finish solving that, you're going to get that our Norton equivalent impedance there is equal to 1.8 plus J 2.4 ohms. So we go ahead and redraw our big chunk of that circuit. We've still got our current source I, that remember is 4 minus J 12 amps. And we've got that in parallel now with our, so 1.8, that's a resistor, 1.8 plus 2.4, so J 2.4. Now that is going to be connected to the rest of the circuit, which is 0.2 connected to J 0.6 connected to 10 ohms minus J 19 ohms. And we still got our terminals sticking out there. So the next thing we need to do is flip it back to a Thevenin equivalent circuit so that we can combine with those impedances up there on the top. So that we'll go ahead and say that we've got our voltage source V that we'll need to calculate here in a second. And that'll be 1.8, J 2.4, 0.2, J 0.6. And as you can see, those will all be connected in series, so that'll be pretty easy to calculate. And 10 and our minus J 19 ohm capacitor. And we're still hunting for that voltage. So we need to use Ohm's law to calculate our V. So V is equal to IR. So that's going to be equal to 4 minus J 12 amps times 1.8 plus J 2.4 ohms. Leave it up to you to finish that arithmetic. And you should get that V is equal to 36 minus J12 volts. So let's see, we can go ahead and start to draw one more circuit. We can combine our series impedances there. So we're going to have just one voltage source, that's 36 minus J 12 volts, connected to, let's see, 1.8 plus 0.2 is just 2 ohms. And 2.4 and 0.6 gets us J 3 ohms. And let's see, that's connected to our 10. And minus J 19 ohm. And remember, we're still looking for that V naught. Now we could do a Norton and then get our parallel impedance there, or sorry, our voltage in parallel, or we could do a voltage divider. And I think I want to do the voltage divider since we haven't really seen many examples of that. So that's, remember, the voltage source times the impedance that we're looking at over the sum. Let's see, so that's V naught is going to be equal to 36 minus J 12 times 10 minus J 19 over the sum 2 plus J 3 plus 10 minus J 19. And when you crunch out all of that algebra, you're going to get our final answer here. That is V naught is equal to, what do we get? 36.12 minus J 18.84 volts. And there is our final answer. So just to recap, we were given a circuit. We wanted to find the voltage on the output terminals of that circuit. And it was a little bit more complex than just doing series and parallel transformation. So we used these Thevenin equivalent circuits and Norton equivalent circuits to sort of chunk it down just like you did in your Circuits 1 class. And that is it for this example. In the next video, we're going to work an example of another circuit analysis technique. We're going to look at the node voltage method. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I'll see you guys in the next lesson. Thank you.